Let's start this revision with mechanical waves. These notes are taken from Foundation of Physics or Physics 1. There are a lot of examples of waves, for instance, ripples in a pond, musical sounds, seismic tremors triggered by an earthquake. If you can imagine at a football game, you have all these people and they're doing the wave. The people themselves are actually just going up and down in their same spot. However, it looks like a wave because everyone is slightly out of sync. So the wave passes through, but each person itself, especially if the wave keeps going passing through, great exercise, but it's very exhausting. Each person is in fact executing simple harmonic motion because they're just going up and down on the spot. There are three types of mechanical waves. The first one's a transverse wave, where the displacement of the particles in the medium are perpendicular to the direction of the travel of the wave. For instance, in this case, you have your particles, they're moving up and down, but the wave is traveling this way. There's a longitudinal wave where the displacement of the particles is medium. In the medium is parallel to the direction. So in this case, it's oscillating this way and transferring energy to that one, which also oscillates around its mean position, and the wave is traveling in the same direction. Then we've got the torsional wave. This is caused by twisting of a metal rod. Well, I've shown it as twisting of a metal rod. Okay. You've actually got twisting and displacing. Okay. We covered these two in Physics 1. So the actual particle itself does not move from its position, only around its position, and energy is transferred from particle to particle. So, common elements. The disturbance propagates with definite speed through the medium. This is called the speed of propagation, or wave speed. It's determined by the mechanical properties of your medium. The medium itself does not travel through space. Its particles oscillate around their equilibrium position, transferring the energy. Because it's a mechanical wave, you have to insert energy. So you have to put in work in order to get this wave going. Okay? The wave motion transports energy from point to point in the median. Now for periodic waves, this is basically where you've got something going up and down and it's continuously sending a pulse through. So you end up having this sinusoidal shape, which is a traditional wave shape. Okay. The periodic transverse wave, which is what we've got illustrated here, this is moving up and down, and the energy moves through this system. Our block moves with simple harmonic motion, and this forms an amplitude, so it's actually displaced by a distance a above and below the mean position. It oscillates f times per second. Okay, and this is just a beaded spring, so we've got little beads on the spring. The result is your periodic disturbance, and it's called a sinusoidal wave, simple as the shape. The distance between 2 points that are exactly the same distance from our mean position and moving with exactly the same speed is called the wavelength. The wavelength is also the distance between two positions that are exactly two crests or two troughs. So that's a trough. The key thing about the wavelength is the 2 points are in phase. Now your speed of the wave is taken as a distance of one wavelength in a time period, so t. So we've got distance taken is wavelength over period, but 1 over your period is also your frequency, so the speed of the wave is given by wavelength times by frequency. Now, all your particles oscillate with the same frequency, so the wave propagates with this frequency. In fact, your particle itself has a period t, in the sense that it goes all the way to the bottom, all the way to the top, and then comes back to the zero position. So your frequency for your wave, or your period for your wave, is the same as your frequency and period of oscillation for the particles that make up your wave. Now, we briefly touched on the mathematical description of the wave. Your mathematical description of the wave, or your wave function, describes the displacement in y of each of its particles at some distance x along the wave at some time t. It is basically a snapshot in time, where you can find out where all your particles are using the wave function. And your wave function is given by y in terms of x and t, with x and t the variables, is equal to the amplitude cos kx minus omega t plus phi, where omega is your angular frequency given by 2 pi f, and k is your wave number given by 2 pi over lambda. So your wavelength and x have got to be in the same unit, so either both be millimeters, both be meters, etc. Phi is your initial phase, or your starting position of your first particle. Now, this here with negative is a wave travelling from left to right, with positive is a wave travelling from right to left. The quantity kx plus minus omega t is called the phase of the wave in radians and is constant. Now, with waves, when they strike a boundary, all or part of the wave is reflected and some of it is transmitted. Now, if it's a fixed boundary, in other words, a hard boundary, when the wave reflects, it comes off with a 180-degree phase change. And if it's a free end, in other words, it is allowed to move, there is no phase change when it reflects. There is one thing that as it does reflect, it will interfere, so you'll end up having an adding of your displacements of your particles at that point.